Okay. Okay, good. So, thanks, Catherine, for the introduction, and to everyone for kicking in numbers up to the very last moment of the workshop. So, I'm standing between you and lunch, between you and the end of the workshop. So, I know this is a delicate situation. So, yeah, no, but my point is, I want to motivate why I will be giving a talk that doesn't have many. Yes, of course, some solid theoretical background, but I will try to be as gentle as I can. A lot of pictures, not many formulas. We'll see how far I can succeed with this. So the title, as you see here, is Multi-index Stochastic Collocation for forward UQ. So it's a topic that is overlapping the first and the second workshop of this program. And I've actually given a talk already on multi-index stochastic collocation last week, but it was a specific talk on a specific problem. And here I want to take a slightly general view on MISC first, and then I want to motivate why it's a good idea to use MISC if you want to solve multidisciplinary UQ problems. So for those who don't know, you can think of MISC, multi-index stochastic collocation, as a multi-fidelity approach to solve parametric PDEs. And if you've never heard of it, you can think of it as an extension of the sparse grid stochastic collocation method, where you add one or more indices in your multi-index set to play with the spatial discretizations. And then I want to focus on, after giving you an introduction to this, I want to focus on multidisciplinary systems. Multidisciplinary systems are problems coming from, let's say, a bunch of realistic applications where you don't have just one PDE you want to solve, but you have several PDEs or a mixture of ODEs and PDEs and algebraic models they constitute a system of many blocks. There's some inputs that go into the block. Each block talks with each other, I don't know, like a fluid structure interaction, or maybe a thermal and mechanical analysis. The two systems communicate with each other. They exchange some information. You want to do UQ on top of this block of systems, okay? So certain random parameters affect block 1, certain random parameters affect block 2. You want to propagate the uncertainty from the whole system to your outputs. And the idea is it turns out to be quite effective. Instead of treating the whole block as a single black box, it's a good idea to build surrogates, MISC surrogates possibly, for each single block, and then put everything together at the end. That saves significantly computational costs. And the main issue is, of course, each of these disciplines exchange some variables, the coupling variables, and you don't know anything about these coupling variables a priori. So you need to figure out how the coupling variables are, and then you learn them as you go, and then that's the technical difficulty here. So let me first start with multi-index stochastic collocation for a single fidelity. So now forget about this multi-fidelity stuff. Multi-disciplines is just one PDE. Let's say that this PDE depends on a bunch of random parameters. Everyone has their own notation. I'm using Z, of course, for inputs. So I have capital N random inputs or uncertain inputs, and the mapping is F. So F is the output of my PDE. It could be the solution itself. It could be a quantity of interest out of that. And my PDE solver depends on a bunch of hyperparameters, R hyperparameters. It could be mesh size, time stepping, tolerances on non-linear solvers. It could be that I have the freedom to play with different mesh sizes along different directions. So I have a 3D problem. I want to have H1 along direction 1, H2 along direction 2. Depending on situation, I have one or more hyperparameters. And I introduce, at this point, you should not be surprised that I'm introducing two multi-indices. One multi-index contains information on how to control the hyperparameters, and the second one contains information on how to sample the uncertain parameters. So the beta is a multi-index in NN, sorry. It's just the usual multi-index for the stochastic collocation on sparse grids. And the alpha just says, take this mesh size, take this time stepping, right? And then F sub alpha beta is the approximation of the PDE over the mesh or the discretization controlled by hyperparameters dictated by alpha and by the sampling dictated by beta. So if I want to solve a PDE over this banana shape, and it's an uncertain PDE that depends on two random parameters, this F sub 416.4,39 means I'm solving 3 times 9 PDEs over a mesh whose discretization is 4 elements in this direction, 16 elements in this direction, and 4 elements in the third direction. So it's the usual combination technique where I'm going to, right? So I will do combination techniques on F of alpha beta. So I need to prescribe how many and which alpha beta I want to use. They will be into a multi-index set I, and then you have the usual combination technique formula. Okay? So this is a combination technique formula, not the usual one on beta only. This is a combination technique on alpha beta. Okay? So, but even if you're a bit lost here, you can just take it as a possibly clever way to do multi-fidelity sparse grid collocation if you want. I'll let this sink in for a moment. And so just this is another slide to convince you. What I'm doing here, I'm taking a problem with one hyperparameter. So maybe you have one mesh discretization parameter and one random variable. So it's a very easy problem. The MISC formula would give me this combination technique. So the solution of the UQ problem would be computed by taking, you see here, this is the set of multi-indices that I can use. Here you read the multi-index alpha. Here you read the multi-index beta. This would be alpha. This would be 1, 1, 2, 1, 1, 2, right? The combination technique formula would tell me my UQ problem can be solved by taking solution P plus solution Q minus solution C. P would be a lot of samples on a coarse mesh. Q would be a few samples on the high mesh. C is a few samples on the coarse mesh. And the combination technique of these three F alpha beta would give me an approximation of F, which would be the final or most accurate solution, okay? But again, this is just to give you some intuition. If you're lost, no worries, because then I'm not really dwelling too much into how MISC works if you want. The final piece of information is that, again, this is just sparse grid, so I can do the usual Gerstner-Griebel adaptive algorithm. This time, the Gerstner-Griebel algorithm has to explore a multi-index set that has an alpha and a beta component. So if I compute forward neighbors of my alpha beta, either I add more samples over the same mesh, because I'm taking the forward neighbor, say alpha beta plus 1, or I'm taking the forward neighbor alpha plus 1 comma beta, so the same samples on the next mesh, okay? Which is very similar to what Helmut was saying yesterday, right? You have these hierarchies of meshes and hierarchies of sampling strategies. This is just a different twist to how we select blocks from that hierarchy of meshes and hierarchy of sampling strategies. But the idea is pretty much the same, okay? And then you compute. This is differently from what, no, different from nothing. This is against the Griebel algorithm, so you have to compute profits, and you iterate once until you're done, okay? So you explore the set of possible multi-indices alpha beta until you get to a certain tolerance, and every time you choose, at every step of iteration, you choose the alpha beta in the reduced margin of I with the highest profit. And the highest profit might be either due to solving on a finer mesh the same samples, or solving more samples on the same mesh. Okay, good enough. And so the idea is that you reconstruct these full approximations, a linear combination of a lot of coarser solutions. And because every time we're testing either refining the mesh or adding more samples, if you do things carefully, you can balance the sampling error and the resolution error. And as I said, I'm saying I'm using a multi-index alpha for the spatial discretization. Alpha doesn't have to be one number, it could be 3 numbers. And then I can play with tensorized solvers, like finite differences. It has, in principle, I have the freedom to choose different number of samples along the 3 spatial dimensions, right? A bit like the picture I was showing you before with this IGA solver with 3 different discretizations along the 3 different directions. We can prove convergence rates for this. They are sort of what you would expect. I'm not dwelling into this too much. But again, I mean, even if you're completely lost here, this is a multi-fidelity black box sampling scheme. This will prescribe me a list of combination of the parameters, a list of meshes, and it will tell me solve this problem on this mesh, this problem on this mesh, this problem on this mesh, and then put everything together, and I get a response surface out of it. Okay, so you can be oblivious of the jibber jabber here, and just this is a multi-fidelity stochastic collocation approach. Now, I have a couple of slides here just to show you that everything works as expected. So here I'm going to show you that I want to solve the usual elliptic PDE with random diffusion, assuming that I have 3 random variables, and I want to solve it in this domain. These are 2 possible different realizations of my random diffusion. In total, I have 6 indices, but I'm playing with 3 discretizations and 3 random variables. So I have a multi-index set of dimension 6. I apply MISC, and I get the convergence that a nice convergence. Here, this is a convergence where I get tolerance here and time, so the flatter is the better, because I can push to small tolerances and my time doesn't blow up. Yes?
I have a quite stupid question. So you prove convergence rates,
yes.
But you only have error indicators, right? So you need saturation assumptions somehow.
Right. Yes. So the convergence rates are not, should have been more careful here. The convergence rates are not for the Gerstner-Griebel algorithm. The convergence rates are if you build your set, the multi-index set a priori, assuming ansatz on the decay of the data contribution.
Yeah, you have convergence rates.
Yes, yes, yes. Of course. Yes. So let's say this is the convergence rate that we prove, and we actually get it. So we're happy. And this would be instead the comparison with multi-index Monte Carlo or multi-level Monte Carlo. So you see that we get substantially better than the other, let's say, sampling methods. Okay. This is a slide where I show you how come we are effective. So where MISC works. I mean, it works because you allocate most of the samples on coarse meshes, but this is not surprising because this is a multi-fidelity method, right? This is just to show you how we allocate, how many samples we allocate on each mesh. Here, so each curve is the allocation of the computation for 1 point. So this point here, the last point of the convergence corresponds to this black curve of allocation work, and the previous point is the blue allocation curve. This means essentially we solve a few thousand PDEs on coarse meshes and only a few hundred PDEs on the finest meshes. Yes.
Is it useful to use levels up to 4?
Levels up to 4? What do you mean?
I was wondering if you say that your level 0 is actually level 4, and you get much worse. I'm worried about this flat.
This flat part here. Yes. Well, okay. So. I would say, well, okay, again, here I'm playing with 3 spatial indices. So in principle, I don't have 8 meshes. I have 1 mesh of 0, 0, 0, 3 meshes of 1, 1, 1, and 5 meshes of, so this is the total mesh index refinement. It means that I'm counting here all the meshes whose alpha multi-index has norm 1. So here I have 3 meshes. This is the number of, I'm locating 100 solves over the 3 meshes, 0, 1, 0, 1, 0, 1. So if you want, this is a smaller, each of the 3 meshes is allocated less solutions than the previous one. So I don't know if that clears up a bit the thing. I think so. Okay. Okay. But now this is the initial part, and I'm done. So this was just motivated. We have a multi-fidelity solver that is multi-fidelity stochastic collocation, that we can get a response surface out of it, that we have a convergence rate, that sometimes we have a convergence rate, and everything was fine, and we can also do the Gerstner-Griebel algorithms to figure out which fidelities to use and how many samples to allocate on each fidelity. Fair enough. Now, the focus of the talk is actually this part, the multidisciplinary problem. So this is a situation where we have a multidisciplinary 4YUQ problem. This is a fire satellite detection problem. So there's a satellite that detects, I don't know exactly what, because I didn't come up with the explication, but so you get measurements on this satellite and want to infer whether there's fire going on somewhere. So this is a system of 3 blocks. This system here is orbit. This describes the movement of the satellite. There's a system, there's an ODE for the power of the satellite. There's another system for the altitude. So it's 3 different ODEs. They exchange some information. So orbit gives some information to power and to altitude. These two exchange some quantities. And each of these 3 ODEs, let's say, also depend on a bunch of random or uncertain parameters. So altitude depends on a number of random parameters, orbit on a number of random parameters, and power on another number of random parameters. So this in total, this is a forward problem from Z1, Z2, Z3 to a certain number of outputs that we get from altitude and power. But if you open up the box, there's 3 little Ds inside, okay? Yes?
Can you just say a bit more about how they speak to each other? It isn't something you can write down as one coupled system. There's somehow separate problems that communicate between.
Yes, so let's say this power is an ODE per se, and the solution, for instance, the solution of power is 1 or 2 quantities of interest of that ODE. So the quantities of interest of that ODE goes into altitude. I can show you another example. I can go straight forward to the end and show you another example, which maybe no, it's okay. No worries. I mean, it might be useful. Okay. So here, this one. This is a gas turbine model. So there's a heat transfer model for a blade of a gas turbine. The solution of the heat transfer is the bulk temperature of the blade. I need this information because I want to estimate the lifetime of the turbine. So Y1 is the bulk temperature of the blade. I need it to estimate the lifetime. The lifetime I need it to estimate how much will be the revenue of the turbine. The revenue depends also on the performance of the turbine. And so the turbine is like a classical PDE, which depends on a bunch of random parameters, diffusion in the metal bulk, the coolant temperature of the 3 fluids that cool up down the blade. And then out of this heat transfer, I compute the bulk temperature of the blade. The bulk temperature of the blade will be as uncertain because it depends on this bunch of uncertain parameters, the red parameters. The bulk temperature goes into the lifetime model for the blade. The lifetime depends on this random parameter PLM, is a coefficient. The temperature, which gives me the failing temperature. The failing temperature goes also into the economics here. So this is the revenue. It's a random quantity, this Fecon, the temperature of failure, and the performance, which depends on another equation, which depends again on a bunch of random parameters. So there's a lot of pieces going on. And each piece has some information from the previous piece and some information coming from the outside as a random parameter. Okay.
This is a different model because like everything goes in one direction, whereas your previous model.
Yes, exactly. Because this is.
I think this was the question.
Yeah, so this is a fully connected, yes, but there are also cases where the 2 things exchange some information in a feedback mode. Yes, exactly. So there's feed forward and feedback. Yes. Now let me go back to where I was. Here. So I have K components or disciplines. Each component depends on a bunch of random variables, ZK. Some of them might be common, by the way, between the different components. The PDF of Z is known because it's an exogenous input. Each of these all disciplines exchange also some quantities. I call them each, let's say here you see them as Y because each component has input Z and output Y, but then the output Y becomes another input for another moment, for another model, and that input now is called Xi. So Xi is a collection of Ys, okay? And the point is these X's are coupling variables and their PDF is unknown because they are the outputs of a system, okay? So the difference, so both Z and Xi are random variables, but Z have a known PDF and Xi have unknown PDF. Okay, and I want to predict the let's say, statistical information on Q, which is the overall output of the system. Okay, and again, certain systems are in feed forward, like so the orbit feeds into power. And in that case, it's very easy to do, right? Sometimes instead, the two systems are connected in feedback mode. And then they have to exchange information. And then what I have to do fixed point iteration between the two things, okay? To get to the equilibrium solution. Good. So what I want to do, I want to do UQ for this coupled system of multi-disciplines. And because, I mean, one PDE is hard enough. Imagine each block is a PDE, right? If I consider the whole thing as a black box, it takes forever because every Z is 3 PDEs, possibly coupled with a feedback mode, okay? So already UQ for one PDE is tough. A UQ for a block of PDEs is even tougher, right? So why don't we do a surrogate model for each block itself, and then we put everything together. So we cut open the loops. We build our surrogate model for each block, and then we put everything together. And that's the idea. The problem is if I want to put everything together, I mean, I don't know the X's. That's the problem. If I knew the X's, I would be able to build the surrogates of each thing, but I don't know the X's. Okay? So that would be the technical issue is how I go about dealing with these X's that I don't know a priori. Okay, this is one piece of theorem that says, of course, here I'm talking about replacing the actual response function of each block with the surrogate. That entails an error. How do the errors of each component propagate throughout the network of models? And it's actually just a matter of taking care of the Lipschitz constants of each block with respect to the coupling variables. I mean, this is no worries. The message here is no worries, everything's under control. Even if you replace each block with its surrogate, as long as each block has an input-output map that has Lipschitz continuity with respect to the X's, everything works fine, okay? So this is not very important. What is more important is this. And this is the only piece the only theorem that I want to give you. The problem is, again, I don't know the X's, I don't know their PDF. What do? Do I really care about the actual PDF of the X's? The answer is no. We don't actually care about the actual PDFs as long as we do a good job in estimating their ranges. So it's pretty safe to replace and treat X's as uniform random variables over their range. So as long as I'm good in getting the range right, it's okay. The PDF doesn't matter too much. And there's a theorem on this that comes from a paper in 2013 by Dongbin and a few other guys. And this theorem is here. It says that the theorem says that the error that I commit by replacing the surrogate built with respect to the exact measure with the surrogate built with respect to an approximate measure as an error that is composed by two terms. One term accounts for the delta. This delta here is the mass of the true measure on the part that the supported were missing. So if I approximate, let's say here, if I approximate the black PDF with the gray PDF, the two are on the same support, and then this term disappears. And the other term here, what is left is a constant times epsilon, and epsilon is the convergence of the surrogate with respect to the true PDF. So if I screw up the PDF, I slow down the convergence by a constant, not by the rate, okay? So I do pay something if I screw up the estimate of the PDF of the Cs, but that doesn't impact the rate of convergence of the overall thing. It just impacts the constants. Okay, so it's safe in a sense. The constant depends on the ratio between the peaks. So if the true PDF is very peaky, and I replace a very peaky thing with a uniform thing, then I'm paying more than if the true PDF is more gentle. That's the takeaway message. Okay, so the theoretical part of the job is done, because replacing each model with its surrogate doesn't impact too much as long as the input output is decent. And even if I don't know the exact C measure, as long as I nail correctly the range, I'm fine. So there's theoretical guarantees that this might work. Okay. How much time do I have? Okay, good. And now the point is, now what I want to do on top of this is I have multiple blocks. I want to build. Okay. So I have multiple blocks. I want to build a response, a surrogate model for each block. I know that it could be a good idea to do on top of doing a surrogate for each block rather than a surrogate for the whole thing. I might want to do multi-fidelity surrogate modeling for each block separately. If these 3 blocks are 3 PDEs, I want to do MISC on one block, MISC on one block, MISC on the other block, and then put the 3 MISC surrogates together, okay? So I want to do the adaptive MISC, so the Gerstner-Griebel algorithm, on 3 blocks separately. And the point is, I want to do this in a good way. So I want to, let's say, play the game of deciding at each iteration, do I really need to refine the 3 meshes, or do I just choose one surrogate that I want to refine and then the other 2 remain constant? Okay. There's a further level of complexity here. So again, I want to do a MISC approximation for each discipline. Which discipline do we refine? So if we want now, it's a MISC with another index. I have kappa, the model, alpha, the mesh, and beta, the sampling. So now it's a MISC++, where I have 3 different chunks of indices. Chunk 1 tells which model I refine. Chunks 2 says which mesh for each component. Chunk 3, how many samples for each model. Okay. This becomes a bit intricate, if you want, so I'm not going to go into the details. But the point is, if I want to decide which model I need to refine, a good idea is to choose which model I want to refine with respect to the overall outcome. So I mean, in general, if I have MISC, in general, I would say I refine each MISC until the output of that submodel is to a prescribed tolerance. But that is not necessarily what I want to do, because here I have multiple models. Maybe I don't need all the models to go to the same accuracy, as long as the total output is under control, right? So instead of doing MISC with respect to the local outputs of each component, I do an error indicator that takes care only of the overall outputs, okay? So that is a good idea, because that it means that I'm more flexible on how much I refine each component. The downside of it is that every time I refine one model, I have to check everything else, because everything is entangled, because what matters is the final outcome, okay? So whenever I refine one model, I have to recompute the profits of every other model. So I have more computations to do at this point. I'm not doing 3 separate MISCs. I'm doing one MISC with one extra chunk, and then everything is related to the very final outcome. So in the standard Gerstner-Griebel, once I compute one profit, that is it. In this case, profits get computed over and over and over because every time I change one thing here, the impact of everything everywhere could change. Like imagine that one model is approximated by a constant. As soon, and that's the, somewhere in the middle. As soon as that thing is no longer constant, the profit of all the upstream components now change because earlier on, those models were completely shut down by the constant, right? Now I have to change everything every time. But that's a technicality. And every time a downstream surrogate can change, we have to do all over again. But that's, other than that, it's pretty much the same Gerstner-Griebel, just we have one extra index that we play. So until the criterion is, until some stop criterion is met, we select the discipline, the model that we want to refine. And for that model, we select the next alpha beta discretization. And we refine MISC only of the model that we selected. And then we recompute all the profits of all the disciplines. But that's this, fair enough. I mean, it's the same idea overall. You just get a bit more convoluted. Imagine the hell of implementing this, right? But other than that, everything was fine. And the other last bit of information is, remember I told you I need to nail down the ranges of the coupling variables that I don't know. The coupling variables are the outputs of each block. Every time I refine the block, I get a more accurate approximation of the outputs of that model. Those outputs are inputs to another model. So, I mean, every time I might want to enlarge the support of the coupling variables, I might find out that my model, at step 1, my model is predicted to model 1 is predicted to output between 3 and 5. Then I refine that surrogate, and now I see that it was not 3.5, it was 3.7. So I have to change that support, and that support means that then if I want to do stochastic collocation with respect to that new support for the second model, now I need to take next points in 3.7 rather than 3.5. It's okay, it's a technicality again. So the point is, if this model outputs something which is supposed to be supposedly into 3.5, then the next input, this is input to the second model. This model has an input between 3 and 5, so I do stochastic collocation with respect to 3.5. Then I improve model 1, and I find out that the model 1 has output between 3 and 7, then the stochastic collocation here should go on 3.7, not on 3.5. Okay, every time I improve one surrogate, I enlarge possibly the range of its output, and then I need to reshape the points on the stochastic collocation of the downstream models. That's another technicality, but we go about that by using Leja points, because even if I start with outputting ranges in 3.5, I put Leja points in 3.5. Then I found out that the range is 3.7. I can put the next Leja point, I can compute it on the new range. I have 3 points in 3.5. The next Leja point is the minimizer of the Leja functional in the new interval. And I keep going like this. That's another technicality. And now results, because I'm done with theory and methodology. So the theory says everything should work because we have, as long as everything is Lipschitz with respect to the X's at least, and as long as I get the ranges of the X's right. So this is an analytic test. Everything is feed forward. The only difference is that Z is input simultaneously to the first and the third. These are just to show that you don't even really need to read this. This is just to show that there's a bunch of sine and cosine exponential. Everything is analytic, okay? So I know everything about this model. So I have everything under control. Now, first results. What happens if, in this procedure that I need to, here I want to convince you that estimating properly the range of variables is important. That if you screw up the support, it doesn't work. And so this is the convergence we're looking at. So here I know everything here. So I know that the ranges of the X's is 0, 1. So if I know that in advance, I get the blue curve. the adaptive procedure where I play with these Leja points, increasing the ranges and blah, blah, blah. It gives me the black curve, which converges up to 10 power minus 12. If I don't do adaptive estimation of the ranges, but I work with the largest range just to be on the safe side, I get this yellowish curve. And if I don't treat each component separately and I do everything one black box, I get the red curve. So you see that there's a dramatic improvement in treating the three models separately rather than doing black box over the big thing. And if instead I don't do the adaptive estimation of the ranges and I just take a range which is not enough, sooner or later I get drifted away. So it doesn't work. And the point where I see the problem depends on how large my interval is. So if the interval is 0,1, if I take it as 0,05, 0,95, I mean, unless I want to push it to really good tolerances, it doesn't really matter. If I'm sloppy in estimating the interval, I get drifted away earlier on. I mean, that's fair enough. Every time because at this point here, sooner or later I will extrapolate. And I have no control what happens when I extrapolate out of my interpolation interval. So every estimation of the ranges works well. This is where the picture is coming from, the picture that I showed you earlier on. This is what happens if I have the previous example that I showed had everything was 1D. So one variable enters, so here, one variables enter here, one from here to here, one here, and one goes here. Now I'm saying, second test, 4 inputs here, 4 inputs here, 4 inputs here, and we exchange more than one output. So this is a higher dimensional problem. And the convergence is this. So there's a first regime where doing black box is better, but sooner or later, this idea of splitting things kicks in, and then eventually we're doing better. And it's not 10 to the minus 7, it's 10 to the minus 2. So there is this is actually convenient in practical regimes, okay? Why is that? Well, because each component has less parameters, right? So the whole thing has 12 parameters, each component has 4 parameters. So approximately something which is 4-dimensional is easier than 12-dimensional. So that's one point. And also if composing models is more expensive, right? So model 1 outputs, model 2 outputs, model 3, the whole thing is a composition of 3 things. If each thing is, I don't know, quadratic, the whole thing is 6th power. And that's more non-linear than each piece, right? So in principle, it pays off to approximate separately each component. This is about multi-fidelity. So this, again, I swept under the rug, but I can also have a multi-fidelity version of that analytic example. So there's some parameters that I can tweak to make it, in a sense, multi-fidelity. So this is the convergence of black box single fidelity, black box multi-fidelity, single box single fidelity open box, multi-fidelity open box. So our approach is the black, and the single fidelity black box would be here, the red. So the gain is impressive, and the message here is that I can allocate work on different components where it matters. So component 1 matters less than component 2 and 3. So I get less work allocated to component 1. And then on top of that, you see that I allocate more work on the coarse fidelities. So I get everything under control. I allocate work where it needs to be allocated, and mostly on coarse fidelities. So that's the dream, in a sense, for a multi-fidelity approach. I only allocate work where it matters, and only on the coarsest fidelities. And now this is the fire detection thing that I was mentioning. This has 8 random inputs and 11 or 7 coupling variables. I'm not even going into what is each thing. We see there's parameters controlling the satellite position, parameters controlling this and that. These are the quantities that are being exchanged by between each submodel. So you see satellite velocity, orbit period is computed by one model and output into the other moment. There's a torque, there's momentum of inertia, blah, blah, blah. Again, this is the standard way of doing it, black box, the red thing. And this is us, this is the black convergence. And here, there's a further level of saving because now we're doing FPI, fixed point iteration, on the surrogates, not on the full models. So I'm doing FPI on polynomials rather than doing FPIs on ODEs. And that also saves a lot of time, right? Because I'm doing these two models are linked in feedback mode. So I need to solve this coupling with fixed point iterations. One thing is to iterate between ODEs, one thing, or PDEs even possibly. One thing is to iterate between polynomials, right? FPI on polynomials takes nothing. FPI on full models takes longer. And here the total cost shows you that. Every time you do an FPI on the ODEs, here it allocates how many PDEs you are solving on each FPI iteration. So that's what happens. And this is a final mode. This is the gas turbine that I was mentioning earlier. The gas turbine is a PDE. The PDE computes the temperature of the blade, fed into the lifetime expectancy. There's a performance model that penalizes certain things and rewards high external things. That doesn't really matter. So the lifetime gets bulk from the PDE and outputs failure temperature, failure time, sorry. Failure time goes into here. This performance gets a bunch of random inputs and gets as output P, this performance. It feeds into this, and this is the final formula. So I have one PDE and a bunch of algebraic models. And what happens is, these are the random variables. Again, it's a bunch of, these are uniform random variables, so a dozen random variables. And this is the convergence that you get. So you see that here, again, black box is over there, and our convergence is down here. So the gain is impressive. The PDE is multi-fidelity, the other one are not. So you can also play with some models having multi-fidelity, other models not having multi-fidelity. And essentially what happens is here that first the model, the overall procedure solves the PDE up to a certain threshold, and then it stops allocating budget here, essentially, and it always works on the downstream components, which are algebraic. And then the cost goes down like crazy because you stopped solving PDEs and now you're just iterating over algebraic quantities. And that is done, actually. So I tried to show this MISC multi-fidelity approximation. We do have convergence proofs in some for some PDEs, for single disciplines. We have a couple of papers on applying MISC to different problems, single discipline. We have a paper on handling multi-disciplines with this idea of decoupling the boxes. And that is it. Thank you for bearing with me.